Welcome to The Explainer. Today, we're jumping right into this massive, high-stakes race to protect, well, our entire digital world from a totally new kind of threat. So it really all boils down to one simple question, but it's a question that has cybersecurity experts and even governments all over the world scrambling. And that is, could a new type of computer actually break the internet as we know it? The short answer? Yeah, it could. And that's exactly what we're going to unpack. All right, here's the game plan for this explainer. First, we're going to define the threat itself. It's got a pretty dramatic name, the quantum crypto-apocalypse. Then we'll figure out the timeline, like how soon is this a problem? After that, we'll look at the new algorithms fighting back, check out the official race to pick the winners, and finally, talk about what we can actually do about it today. Okay, let's get right into it. To really understand what's going on, we first have to get a handle on why these quantum computers are such a massive deal for, all of our digital security. The difference between the computer on your desk and a quantum computer, it all comes down to bits versus qubits. See, a normal computer bit is simple. It's either a 0 or it's a 1. End of story. But a qubit can be a 0, a 1, or, and this is the wild part, it can kind of be both at the exact same time. This is called superposition, and it lets a quantum computer check out a ton of possibilities all at once, which makes it unbelievably powerful for certain problems. So what's so interesting here is that this reveals the quantum computer's secret weapon. It's an algorithm called Shor's algorithm, and it just so happens to be perfectly designed to solve the exact kind of math problems that our most common encryption relies on. The stuff that protects websites, your bank transactions, digital signatures, all of it. For a big quantum computer, Shor's algorithm makes breaking these codes look like child's play. And it doesn't stop there. There's another quantum algorithm, Grover's algorithm, that goes after a different kind of encryption, what we call symmetric encryption, things like AES, that we use to protect huge amounts of data. Now, it's not as totally devastating as Shor's, but what it does is it effectively cuts the security in half. It's like taking a really, really strong lock and just snapping off half of its strength. So this all sounds pretty serious, right? But if these super powerful quantum computers aren't here yet, how much time do we actually have? I mean, when should we really start to worry about this? Thankfully, a cryptographer named Michele Mosca gave us this really brilliant, simple way to think about it. It's called Mosca's theorem, and it's a little formula that says if x plus y is greater than or equal to z, then yeah, you need to be worrying right now. Okay, let's unpack that formula. X is all about your secrets. How long do they need to stay secret? Are we talking about national security data that has to be safe for 50 years? Or just an email that's irrelevant tomorrow? Then there's Y. That's how long it's going to take you to upgrade everything, your servers, your software, the whole shebang. And Z? Well, Z is the big unknown. That's how many years we have until one of these crypto-breaking quantum computers actually gets built. And this slide really shows you just how complicated that Z part of the equation is. Building one of these things is incredibly hard. It's like a 7-stage rocket launch. And while nobody's gotten to the final stage yet, you've got huge players, tech giants, governments pouring billions of dollars into this. The estimates for Z are all over the place, from 10 years to maybe never. But the point is, progress is being made. And for any data that needs to stay secret for a long, long time, that clock is already ticking. Okay, so we've got the problem. We've got the timeline. Now for the good news. Cryptographers have not been just sitting around. They've been busy creating whole new families of algorithms specifically designed to stand up to both the computers we have today and the quantum computers of tomorrow. So you've got a few main families of these new algorithms. Some are based on ideas we already trust, like hash-based methods, and some are based on totally different, really hard math problems, like code-based and lattice-based cryptography. They're all trying to solve the same problem from different angles. But here's the thing, and this is super important. There is no silver bullet here. There's no single perfect replacement. As you can see on this chart, every option comes with trade-offs. Take Miceli's, for example. Super trustworthy, it's been around forever, but the key sizes are huge. We're talking like a megabyte. Then you have others, like Sphinx, with smaller keys, but really big digital signatures. It's a constant balancing act between security, speed, and size. So if you've got all these different options and they all have different pros and cons, how in the world do we decide which ones to use? I mean, who makes that call for everybody? Well, that's where the race to standardize comes in. That's where the U.S. National Institute of Standards and Technology, or NIST, comes in. Back in 2016, they basically fired the starting gun on a huge worldwide competition. They invited cryptographers everywhere to submit their best ideas, which would then go through years of intense public scrutiny before any of them could be crowned a new standard. And the key thing to get here is that this is not a quick process. This is a marathon, not a sprint. This whole multi-year process, with experts from all over the world trying to break these algorithms, is absolutely essential. We have to be confident they're secure before we start using them to protect, everything. And you know how serious this was? Even before NIST kicked things off, the NSA put out this pretty shocking advisory. They basically told everyone, hey, don't bother upgrading to the next version of our current crypto. Just skip it. Start preparing for the post-quantum stuff instead. That was a massive signal to everyone to leapfrog directly to the next generation of security. Okay, so this brings up a huge practical question, right? The threat is coming, but the new standards from this big NIST PQC process, they're not quite finalized yet. So what are you supposed to do right now if you have data that needs to stay secret for a long time? The answer, and the strategy pretty much everyone is recommending, is something called a hybrid scheme. It really is the best of both worlds. You take a classic algorithm that we know and trust today, like ECDH, and you combine it with one of the new post-quantum contenders. The beauty of this is that an attacker has to break both of them to get to your data. They'd have to crack today's crypto and tomorrow's crypto. It's a really smart way to bridge the gap. And this is the final thought I want to leave you with. The biggest risk right now isn't that a quantum computer will appear tomorrow and break things. It's the idea of harvest now, decrypt later. Adversaries can be recording all our encrypted data today and just storing it, waiting for the day they finally have a computer powerful enough to crack it all open. So the real question you have to ask yourself is this: in a quantum future, which of your secrets will survive?